We start with a historic mission to the moon and the launch of India's Chandrayaan-3 spacecraft.
So the question is, what exactly will Chandrayaan-3 do if it makes a successful soft landing to the moon's south pole?
Landing a rover on the moon is no small feat that only a few countries can boast of. India has joined the exclusive club with its own moon rover. But that is not even the biggest thing, because the new discovery on the moon by the Asia nation changes everything we thought we knew about the moon. What has India discovered, and why is every scientist excited about it? Stay tuned to find out. Sending rovers to the moon started with the Soviet Union, beating the United States by a few months. The rover was called Lunokhod-1, which means moonwalker in Russian. Lunokhod-1 was launched on November 10, 1970, and landed on November 17, 1970, in the Mare Imbrium region of the Moon. It was carried by an unmanned spacecraft called Luna 17, which also served as a communication relay. Lunokhod-1 was a self-propelled vehicle that had 8 wheels, 4 cameras, an X-ray spectrometer, a laser reflector, and other instruments. It was powered by solar panels and a radioactive heat source. It was controlled remotely by operators on Earth using a joystick and a video monitor. Lunokhod-1 operated for 322 days, covering a distance of 10.54 kilometers or 6.55 miles, and sending back over 20,000 images and 200 TV transmissions. It also performed 25 soil analyses and measured the magnetic field and radiation levels of the moon. Lunokhod-1 exceeded all expectations and became a symbol of Soviet technological prowess and scientific curiosity. It paved the way for future lunar missions and inspired generations of space enthusiasts. As mentioned earlier, the US was the second country to land a lunar rover on the moon. The rover was called the Lunar Roving Vehicle, or LRV, or simply the Moon Buggy. The LRV was launched on July 26, 1971, and landed on July 30, 1971, in the Hadley Apennine region of the Moon. It was carried by the manned spacecraft Apollo 15, which was the 4th lunar landing mission. The LRV was a 4-wheeled vehicle that had 2 cameras, a navigation system, a communications antenna, and other instruments. It was powered by 2 batteries and could travel up to 13 kilometers per hour or 8 miles per hour, ensuring it wouldn't win any racing competition. It was driven by the astronauts using a T-shaped handle and a foot pedal. The LRV operated for 3 days, covering a distance of 27.76 kilometers, or 17.25 miles, and sending back over 6 hours of video and audio transmissions. It also helped the astronauts collect 77 kilograms, or 170 pounds of lunar rocks and soil samples. The LRV was a breakthrough in lunar exploration, as it allowed the astronauts to explore more terrain and conduct more scientific experiments than ever before. It also enhanced the public interest and excitement about the moon missions. There is a new member in this club of moon rover owners, namely India. India has achieved a remarkable feat by successfully landing its Chandrayaan-3 spacecraft near the moon's south pole, becoming the first nation ever to do so. This historic mission has not only demonstrated India's prowess in space exploration, but also opened up new possibilities for scientific discovery and human exploration of the lunar surface. Chandrayaan-3, which means moon vehicle in Sanskrit, is India's 3rd lunar mission and the most ambitious one yet. It consists of 3 parts: a lander named Vikram, a rover named Pragyan, and a propulsion module that carried them to the moon. The spacecraft was launched on July 14, 2023, from the Satish Dhawan Space Center in Sriharikota, Andhra Pradesh. After a journey of about 384,400 kilometers, or 238,855 miles, it reached the moon's orbit on August 6th. The most challenging part of the mission was the final descent and landing of the Vikram lander, which had to perform a series of complex maneuvers to avoid obstacles and find a suitable spot to touch down. The lander had to reduce its speed from about 6,000 kilometers per hour, or 3,728 miles per hour, to 0 in just 15 minutes using its thrusters and sensors. This phase, dubbed 15 Minutes of Terror by ISRO Chief K. Sivan, was executed autonomously by the lander's onboard computer without any human intervention. The lander successfully completed its descent and landed near the south pole of the moon at 1804 India time on August 233. The control room at ISRO erupted in cheers and applause as the confirmation of the landing came through. Prime Minister Narendra Modi, who was following the launch by video link from South Africa, where he was attending the BRICS summit, declared, "India is now on the moon, and the sky is not the limit," as he congratulated the ISRO team and the nation. The lander has already sent back some stunning images of the moon's surface, showing its rocky and cratered terrain. The next step is to deploy the Pragyan rover, which is tucked inside the lander's belly. The Pragyan rover is a marvel of engineering and science, designed to explore the lunar surface and reveal its secrets. It is a rectangular chassis with dimensions of 0.9 by 0.75 by 0.85 meters. It weighs about 27 kilograms or 60 pounds and operates on solar power. It has a solar panel that can generate 50 W of electricity. The Pragyan rover has 6 wheels, each driven by independent brushless DC electric motors. The wheels have a rocker bogie suspension system, which allows the rover to adapt to the uneven terrain of the moon. The rover can travel at a speed of 1 centimeter per second or 0.36 kilometers per hour and cover a distance of 500 meters or 1,600 feet in its planned mission duration of 14 Earth days. The Pragyan rover has 2 cameras and 2 instruments to perform scientific experiments on the lunar soil. The cameras are called navcams, or navigation cameras, which provide a stereoscopic view of the surroundings and help in path planning by generating a digital elevation model of the terrain. The instruments are called APXS, or alpha particle X-ray spectrometer, and LIBS, or laser-induced breakdown spectroscope, which measure the chemical composition of the soil by using alpha particles and laser beams, respectively. The Pragyan rover communicates directly with the Vikram lander, which relays the data to the Earth station. The rover has antennas for this purpose. The rover also has sensors to measure the temperature, pressure, density, and magnetic field of the lunar environment. The main objective of Chandrayaan-3 is to study the south polar region of the moon, which is largely unexplored and holds great scientific and strategic interest. Scientists believe that this region may contain water ice deposits in its permanently shadowed craters, which could be used for supporting human habitation or supplying propellant for future spacecraft. The mission also aims to map the topography and mineralogy of the region, as well as test new technologies for lunar exploration. With this mission, India has joined a select group of countries, the US, Soviet Union, and China, that have successfully landed a spacecraft on the moon. Chandrayaan-3 is the first mission to land near the south pole of the moon, which is largely unexplored and holds great scientific and strategic interest. Scientists believe that this region may contain water ice deposits in its permanently shadowed craters, which could be used for supporting human habitation or supplying propellant for future spacecraft. The mission also aims to map the topography and mineralogy of the region, as well as test new technologies for lunar exploration. Chandrayaan-3 is the cheapest lunar mission ever, with a budget of only Rs 615 crore or about $82 million. For comparison, Russia's Luna 25 costs roughly Rs 1,600 crore or about $214 million. America's Apollo 11 cost way more than that since it was the first manned moon mission back in 1969. Interestingly, Chandrayaan-3's Rs 615 crore budget is less than the recently released movie Adipurush. Adipurush's budget was around Rs 700 crore or about $94 million. The Chandrayaan-3 mission faced a lot of challenges, including technical and logistical challenges. The launch window was very narrow, as the mission had to take advantage of the favorable alignment of the Earth, Moon, and Sun. The launch had to be precise and timely, as any delay or error could jeopardize the mission. The landing site near the south pole of the moon was difficult to access and navigate, as it had rugged terrain, high slopes, deep craters, and extreme temperatures. The lander had to perform a soft landing in a safe and flat area, avoiding any obstacles or hazards. The communication between the lander, rover, and Earth station was challenging, as the south pole of the moon was not always visible from the Earth. The lander had to relay the data from the rover to the Earth station using its high-gain antenna. The communication also had to be secure and reliable, as any interference or loss could affect the mission. The rover had to operate autonomously, as it could not receive real-time commands from the Earth station due to the long delay in communication. The rover had to use its onboard computer, sensors, and cameras to plan its path, avoid obstacles, and perform experiments. The rover also had to cope with the harsh lunar environment, such as dust, radiation, and thermal variations. The mission had to be cost-effective and innovative, as India had a limited budget and resources for space exploration. The mission had to use indigenous technologies and components, such as the solid-state reaction method, to create the superconductive material LK-99. The Chandrayaan-3 is an amazing continuation of India's previous missions to the moon, which have unearthed many groundbreaking discoveries. The Chandrayaan-1 mission was a historic achievement for India and the world, as it revealed the presence of water molecules on the moon. The Chandrayaan-1 mission was launched on October 22, 2008 by the ISRO. It was India's first deep space mission and the first Indian spacecraft to reach the moon. The mission had two main objectives: to orbit the moon and to send an impactor to the surface. The orbiter carried 11 scientific instruments from India and other countries, including NASA's Moon Mineralogy Mapper, or M3, an imaging spectrometer that could detect minerals and water on the moon. The impactor, called the Moon Impact Probe, or MIP, was a 35 kg cube-shaped device that carried a radar altimeter, a video imaging system, and a mass spectrometer. The MIP was released from the orbiter on November 14, 2008, and crashed into the Shackleton crater near the lunar south pole. The MIP was the first Indian object to land on the moon, and it sent back valuable data during its descent. The mass spectrometer, called Chandra's Altitudinal Composition Explorer, or CHASE, detected traces of water vapor in the lunar atmosphere. This was the first direct evidence of water on the moon, and it was announced by ISRO a few months before NASA's announcement in September 2009. The M3 instrument on the orbiter also played a crucial role in confirming and reconfirming water on the moon. The M3 used spectroscopy to analyze the light reflected off the lunar surface. By studying the light, scientists were able to determine that there were water molecules or hydroxyl groups, a hydrogen-oxygen chemical bond, present in the top layer of the lunar soil. The M3 data was corroborated by observations from other spacecraft, such as NASA's EPOXI and Cassini, and ISRO's hyperspectral imager. The M3 also directly measured the distinctive way that water ice absorbs infrared light, so it could differentiate between liquid water, vapor, and solid ice. The M3 data showed that water ice was patchily distributed in the polar regions of the moon, and that it could be ancient. The discovery of water on the moon was a major breakthrough for lunar science and exploration. It opened up new possibilities for future missions and human settlements on the moon. One of the main objectives of Chandrayaan-1 was to map the lunar surface, especially the South Pole region, which is of interest due to the possibility of finding water ice in permanently shadowed regions. Chandrayaan-1 carried 11 scientific instruments, 5 of which were developed by India and 6 by other countries, including NASA, ESA, and ISRO. Among these instruments, the Terrain Mapping Camera, or TMC, and the Miniature Synthetic Aperture Radar, or MINI-SAR, were crucial for mapping the lunar South Pole. The TMC was a high-resolution camera that captured images of the lunar surface in visible light. It had a spatial resolution of 5 meters and covered a swath of 20 kilometers. The TMC provided data for creating a 3D map of the moon, which helped in understanding its topography, morphology, and geology. The TMC also identified several new features on the moon, such as impact craters, lava tubes, and rills. The MINI-SAR was a radar instrument that operated in the S-band frequency. It had a spatial resolution of 150 meters and covered a swath of 18 kilometers. The MINI-SAR was designed to detect water ice deposits in the polar regions of the moon by measuring the radar reflectivity and circular polarization ratio, or CPR, of the surface. the mini-SAR detected several anomalous high CPR regions in the South Pole, which indicated the presence of water ice or other materials with high dielectric constants. The TMC and mini-SAR data were combined to create a comprehensive map of the lunar South Pole region, which revealed its complex geology and potential resources. The map showed that the South Pole region is dominated by impact craters of various sizes and ages, some of which are permanently shadowed and may harbor water ice. The map also showed that the South Pole region has diverse terrains, such as highlands, mare basalts, pyroclastic deposits, and ejecta blankets. The map also helped in identifying potential landing sites for future missions, such as Chandrayaan-2 and Artemis. The map also provided valuable information for scientific studies, such as lunar evolution, cratering history, volcanism, tectonism, and regolith formation. Chandrayaan-2, which was launched in 2019, however, discovered something else: mini-moon craters. The mission consisted of an orbiter, a lander, Vikram, which unfortunately crash-landed, and a rover, Pragyan. The orbiter carried 8 scientific instruments, one of which was the Terrain Mapping Camera 2 or TMC-2. The TMC-2 was a high-resolution camera that captured images of the lunar surface in visible light. It had a spatial resolution of 0.5 meters and covered a swath of 20 kilometers. The TMC-2 provided data for creating a 3D map of the moon, which helped in understanding its topography, morphology, and geology. One of the remarkable findings from the TMC-2 data was the discovery of mini-moon craters, which are small impact craters with diameters ranging from 1.5 to 10 meters. These craters are much smaller than the typical lunar craters, which have diameters of tens to hundreds of meters. The mini-moon craters were detected in various regions of the moon, such as the Mare Imbrium, Mare Serenitatis, Mare Tranquillitatis, and Oceanus Procellarum. They were also found near larger craters, such as Copernicus, Tycho, and Aristarchus. The mini-moon craters are significant for several reasons. First, they provide insight into the moon's resurfacing processes, such as impact cratering, volcanism, tectonism, and space weathering. The mini-moon craters indicate that the lunar surface is constantly bombarded by small meteoroids, which create fresh ejecta and expose new materials. Second, they reveal the diversity and complexity of the lunar regolith, which is the layer of loose dust and rocks covering the lunar surface. The mini-moon craters show that the regolith has different properties depending on the location and depth. For example, some mini-moon craters have bright ejecta, while others have dark ejecta. Some mini-moon craters have smooth floors, while others have rough floors. Third, they offer potential sites for future exploration and utilization of the lunar resources. The mini-moon craters may contain valuable minerals and volatiles, such as iron, titanium, silicon, oxygen, hydrogen, and water. These resources could be used for scientific research, in situ resource utilization, or ISRU, or human settlement. The Chandrayaan-2 mission also helped us learn more about the moon's surface temperature and mineralogy, which are crucial for understanding its origin and evolution. The radioanatomy of moon-bound hypersensitive ionosphere and atmosphere, or RAMBA instrument, measured the surface temperature of the moon at different locations and times. It also studied the variations in the lunar ionosphere and atmosphere, which are influenced by solar radiation and cosmic rays. The Imaging IR Spectrometer (IRS) instrument detected the signatures of various minerals and molecules on the lunar surface. It also mapped the distribution of water, hydroxyl, and other volatiles, which are important for future lunar missions and colonization. The Orbiter High Resolution Camera (OHRC) instrument provided high-resolution images of the lunar surface, which helped in identifying the geological features and structures. It also assisted in selecting the landing site for the Vikram lander and the Pragyan rover, which unfortunately failed to land successfully. The Chandrayaan-2 Large Area Soft X-ray Spectrometer class instrument measured the abundance of major elements such as magnesium, aluminum, silicon, calcium, titanium, iron, and sodium on the lunar surface. It also detected traces of chromium, manganese, nickel, and cobalt, which are indicative of the moon's magmatic history. The Solar X-ray Monitor (XSM) instrument monitored the solar X-ray flux and its variations, which affect the fluorescence emission from the lunar surface. It also calibrated the class instrument and provided data on the solar activity and its impact on the lunar environment. China, however, will not be outdone by India in lunar exploration. China's Chang'e missions have revealed some shocking discoveries about the moon that challenge our previous understanding and raise new questions. One of the most shocking discoveries made by China's Chang'e missions is the presence of young volcanic rocks on the lunar surface. The Chang'e-5 mission, which returned to Earth in December 2020 with 1.7 kilograms of lunar samples, was the first to collect rocks from a site called Oceanus Procellarum, a vast plain on the near side of the moon. The analysis of these samples showed that they were basaltic rocks formed by solidified lava flows, and that they were only about 2 billion years old. This is much younger than the rocks collected by the Apollo and Luna missions, which were all over 3 billion years old. It also implies that the moon was volcanically active for much longer than previously thought, and that there might have been different sources of heat that sustained this activity. Another shocking discovery made by China's Chang'e missions is the detection of hidden structures beneath the far side of the moon. The Chang'e-4 mission, which landed on the far side of the moon in January 2019, was equipped with a ground-penetrating radar that could probe up to 40 meters deep into the lunar soil. The radar data revealed that the top layer of the lunar surface was composed of multiple layers of dust, soil, and broken rocks, and that there was a large crater buried underneath. The crater was likely formed by a massive impact that shattered the lunar crust and exposed the mantle. The radar data also showed that there were 5 distinct layers of lunar lava beneath the crater, indicating that there were multiple episodes of volcanic eruptions that covered the impact site with molten rock. These eruptions might have been triggered by the impact itself or by other factors, such as tidal heating from Earth's gravity. A third shocking discovery made by China's Chang'e missions is the evidence of meteor strikes on Earth recorded in the lunar rocks. The Chang'e-5 samples contained traces of noble gases such as helium and neon, which are usually implanted by solar wind or cosmic rays into lunar rocks. However, some of these gases had unusual isotopic ratios that did not match those expected from solar or cosmic sources. Instead, they matched those found in Earth's atmosphere. This suggests that these gases were transferred from Earth to the moon by meteorites that hit our planet and ejected some material into space. By measuring the amount and age of these gases in the lunar rocks, scientists can estimate when and how often Earth was bombarded by large meteors in its past.